Hello, my name is Akbar Saeed, and I'll be presenting this paper today called Optimization of Reconfigurable Intelligence Services through Trace Maximization. So what are reconfigurable intelligence services? Well, it's basically an engineered surface that can shape the amplitude, phase, frequency, or polarization of the instant electromagnetic wavefront before re-emitting it. So as shown here, there are these RISs on the surfaces of building reflecting signals. And there's a lot of work on RISs recently based to enhance the connectivity, range, capacity, or energy efficiency of future wireless networks. So here's a setup we have. We're going to consider an RIS-enabled point-to-point MIMO communication link. So we have a transmitter, which has a ULA. We'll focus on ULAs, uniform linear array, with NT elements that transmits to an RIS with NS elements, and then the receiver has NR elements ULA. So the transmitted signal X goes to the propagation channel H. That's a received signal, incident signal on the RIS, and the output signal is shaped by the IRS matrix phi, and that goes through the propagation channel matrix G to the receiver. So the final signal is Z, received signal is Z equals G phi HX, and the G phi H is the composite transmit RS receiver link matrix, and this is additive white Gaussian noise. And our goal is to design the psi. So how do we model the channel component matrices? Well, we'll do actual multipath propagation channels. Our focus is on spatial multipath channels. So there's no selectivity in time or frequency. So each of these two channels are modeled as multipath propagation channels with NP paths, complex path gains, and then spatial frequency corresponding to the angle of arrival, which is here, and this is the angle of departure of the transmitter, and this is a column vector, and this is the row vector. These vectors are the steering vectors, response vectors, which are spatial sinusoids, parameters by the spatial frequency, which is related to the actual angle through this half sine phi relationship for half wavelength space antennas. We'll consider both line of sight and non-line of sight propagation. We assume that there's no direct path between transmitter and receiver, so that all communication goes through the RIS. And we'll consider both rich and sparse multipath environments. So here's the problem formulation. Our goal is to design the RIS matrix phi, which we formulate as the RIS matrix that maximizes the trace of F Hermitian F, subject to the constraint, which is basically a trace constraint on the RIS matrix to preserve power. So why are we maximizing trace? Well, if you look at the received signal power, average received signal power, you find that it is, if you assume that independent signals, equal power signals are on the transmitters, this received power is proportional to the trace of F Hermitian F times the average power on each transmit dimension. So maximizing the trace of F Hermitian S is equivalent to maximizing the average received power. So for the IRS matrix phi, this is NIS by NIS matrix, and we'll consider three possibilities. First is a baseline unengineered RIS design, which corresponds to any natural surface where the matrix could be the identity or a diagonal matrix with the random entries, phases, or amplitudes. And then we'll also consider a low complexity phase only design based on reference 9 in the paper. And our optimization is going to be for either diagonal or a full general psi matrix, and we'll talk about that. These first two designs are both diagonal. So let's look at the optimum diagonal solution. So this is again the optimization problem, maximize trace F Hermitian A subject to the trace constraint on the phi matrix. So let lowercase phi be a vector with diagonal entries for the RIS matrix. So then you can write the composite link matrix in terms of the diagonal entries of the RIS and the column vectors of matrix G and the row vectors of matrix H. And so in this case, it turns out that the optimum solution for diagonal phi is a scale version of the dominant eigenvector UK corresponding to the largest eigenvalue of K, where K is this matrix, which is determined by the inner products between the rows and columns of H and G. And then you put them, take the diagonal vector and put it in the diagonal entries. The proof follows from the fact that the trace, if you expand it out, it takes this double summation, and then you change the order of entries in the trace. These become scalars, and eventually we get this quadratic form in this matrix K. So the dominant eigenvector maximizes the trace. Now the general solution, which is not diagonal, again, the same optimization problem, but now we vectorize F, the composite matrix, column-wise, and we apply well-known identities in terms of Kronecker products. So this can be written as H transpose Kronecker G vectorized version of the matrix phi, which we call psi. And so you get this representation. And now it turns out in this case also the optimum solution is a reshaped, in other words, vector to matrix representation of a scale version of the dominant eigenvector Vm, corresponding to the largest eigenvalue of M, where M is now H Hermitian, Kronecker G, complex transpose G. So notice that this is NT-NR by NT-NR matrix. And so when we do the reshaping, or NIS by NIS matrix, and when we do the reshaping, we get that. So the proof again follows from the looking at the trace. Now we expand it again using the Kronecker identities. You get that in the end, it's again a quadratic form involving this matrix M, which is NIS squared by NIS squared matrix, which you reshape into this. Okay, and this is a more general version where you get the input signal and then multiply it with a full matrix before you're retransmitting it. So this would require the new engineering of the IRS. So one way is to have interleave elements, blue, for example, for the received signals and red for the re-emitted signals. Now we'll also compare it to two designs, low complexity phase only design and the baseline. So the baseline design, again, which you'll call random, could have either the diagonal random phase entries or random amplitude and phase entries. And the low complexity phase only design is based on a reference 9, and the diagonal entries are based on phase matching at the G matrix and H matrix. And these tildes are the absolute values of the vectors of the two matrices. And we can design this way. So let's look at some numerical results. So we have a 28 gigahertz system, millimeter wave, 6-inch linear apertures, or ULAs at the transmit, receive, and RIS. This corresponds to 29 half-wavelength space elements. And we'll also consider the impact of a larger RIS, which is 9-inch, and that corresponds to 43 elements. We'll compare 5 designs: the optimum diagonal, optimum general, low complexity phase only, and baseline with complex random entries or just random phases. We consider both non-line of sight and non-line of sight plus line of sight propagation. In the line of sight case, the LOS path is 10 dB stronger than the other non-LOS paths. We'll consider sparse multipath with 10 paths, rich multipath with 100 paths. The average power in the channels is going to be kept constant. And the number of spatial channels that can be established as minimum of the NTNR NIS, which is 29. And we'll parameterize the capacity as receive SNR per channel, average receive SNR per channel, which is P average time the expected trace divided by N channel. And we'll assume for the optimum design and the low complexity design, the perfect knowledge of A, G, and F at all 3 places, transmit, receive, and RIS. So here is the channel power comparison. So this is, the columns are non-line of sight plus line of sight, and non-line of sight plus line of sight corresponding to the larger RIS. So these are the columns. Top row is rich, sparse multipath, bottom is rich multipath. So if you look at non-line of sight component, you can see that the low complexity phase only and random baseline designs have about the same channel power. These are the realization indices of the channels. Whereas the optimum diagonal has higher power, which is expected, and the optimum general has the highest power. If we go to rich scenario, multipath scenario, what you see is that the variation of the power gets lower because of the higher diversity in the channel. But the average powers for the RAN and low complexity phase only are about the same, whereas the powers for the optimum designs actually get a little bit smaller, and we'll see um, the optimum designs favor fewer eigenvalues. If you add a line of sight component, which is 10 dB stronger than the non-line of sight, what you see is that again, the low complexity phase only and random the power is about the same fluctuations. The optimum diagonal matrix has a surprisingly low variation. And then the optimum general has more variation, but again, the powers are slightly about the same. Maybe the optimum diagonal is a little bit higher. And if you go to rich multipath, we see the same trend. All the optimum powers go a little bit down because of the richer multipath. And if you increase the size of the RIS, all we see is the increase in the powers for all of them. So even low complexity phase only design, and then in particular the optimum designs. And again, if you go to the richer scenario, the relative powers go down. Now let's look at, excuse me, the channel eigenvalues. Again, the same setup. If you look at non-line of sight, when there are 10 paths, the low complexity phase only design and the optimum general designs follow a very similar trend of eigenvalues, ordered eigenvalues, except that the optimum design has one, the first eigenvalue is a little bit stronger. And if you look at the optimum general design, its strongest eigenvalue is even higher, and the rest of the eigenvalues are smaller. And notice that these 10 dominant eigenvalues correspond to the presence of 10 paths. If you go to rich multipath, now the eigenvalues for low complexity RAN and optimum diagonal are distributed over the entire spatial signal space because we have more paths, but the general trend is the same. If you go to non-line of sight plus LSI, again, the same trend applies, but the dominant eigenvalues are slightly higher because of the line of sight component. And then if you go to large RIS, against the same trends, but the dominant concentrated eigenvalues get even larger. So the optimum designs tend to focus the energy in fewer eigenvalues. Now let's look at the capacity comparison. So here is the non-line of sight sparse case. So the first we note is that both low complexity phase only and RAN are about the same. Optimum diagonal gives the same capacity at higher SNR per channel, but gives us a capacity gain, significant gain at lower SNR. And the optimum general gives an even bigger low SNR gain, but at the cost of loss in capacity in higher SNR. So there's a trade, crossover point. If you go to rich multipath, the trends are the same, except that the gains get a little bit smaller at lower SNRs, and the loss for optimum general design is even more significant, and the crossover points move to the left. Same trends happen here. Crossover points moves to the left when we have a line of sight component here as well. But notice that the gain in capacity in low SNR is actually increased because of the optimum designs. And then this crossover point moves a little bit to the right. And when you increase multipath, again, the same thing happens, that the gain in capacity gets smaller. Now, if you increase the RIS, what you get is these two components get even higher at lower SNRs. And when you go to rich multipath, again, the same thing. You get a loss in capacity, maybe not as bad as here, but the general trends remain the same. And finally, we want to show that even the phase-only versions, if you look at the phase-only version of the optimum design, they give actually pretty comparable performance. In fact, in some cases, they even give an increase in capacity, which is very relevant from a practical perspective. So just to conclude, the optimum designs tend to concentrate channel power into fewer eigenvalues, and they lead significant capacity improvement at lower SNRs. Capacity gains are higher in sparse multipath and our presence of line of sight path. Phase-only versions are also very competitive and incur no loss in capacity loss, so that's good. And the baseline and low complexity phase-only designs are very comparable. Now, this paper opens new directions for research, including probability of error analysis, time and frequency selective channels, multi-user networks, and channel estimation. And so I'll stop there, and I hope you read our paper. Thank you.